Well, hello and welcome back to another episode. It's great to see you all. I hope you're doing well. So today we're continuing with our series on writing a ray tracer in C++ using only the standard libraries and the SDL2 libraries so we can display things in a window. And specifically today I want to talk a little bit about materials and how we can implement basic materials that we can apply to our objects. So far we've created a very simple scene that consists of spheres and planes, the staple of any ray tracing tutorial because they are the easiest shapes to do. We are going to go on to look at different shapes soon, I promise. But for now that's what we've got. And what we're going to look at today is how we can extend that to, as I say, model a little bit more detail about how, or model in a little bit more detail about how the light interacts with the surface of our object, so we can have things like reflectivity and specular highlights as well as the diffuse shading that we have already. So hopefully that will be of interest. Anyway, just before I jump into that, I'd just like to say, as I always do, that if you do like this video, please do remember to hit that like button. It really does help with the YouTube algorithm, and if you haven't done so already, please consider subscribing to my channel so that you don't have to miss any future videos. Thank you very much. Right, without much further ado, let's jump to it and let's talk about how we can implement basic materials. Okay, so here we are, episode 7 already. It's gone rather quickly for me. Perhaps my rate of producing videos has been slower than you would have liked, but there we go. So anyway, episode 7, basic materials. Now, this is our objective. This is the final image that we're aiming to achieve at the end of our episode today. And you can see a number of things going on here. We've got reflections and things that we had before, and the diffuse shading that we had before, but now you can also see that we have reflections. The various objects are reflecting multiple times across each other, and we have specular highlights, as you can see here. So those are really the extensions that we're going to do compared to what we've had up to now. So just to summarise, we're only going to consider simple materials at the moment. We're not yet going to talk about physically based rendering or anything like that. That might be something I go on to do in a later video. I'm not promising. We'll see how things go and see how much interest there is, but that's possibly something we could look at in the future. But we are still building an approximate model for how light interacts with the surface of an object. And initially we're going to consider materials with just 3 components. The diffuse colour component that we've already modelled in a very simple way, the specular highlights or specular colour component, and also reflection. And we're going to do this using the most basic model, which is known as the Phong model, particularly for the specular highlights. We're sticking with doing diffuse colour the way I've done it in the previous videos where we talked about that, but we're going to use the Phong model when we come to look at specular highlights, which is, it has to be noted, not the only way of doing it, and it is probably the most basic, which is why I thought it would be the most appropriate for this video. And we're going to look at reflection, which requires doing a bit of recursion as well, so that should be interesting. And then we make other topics such as refraction to make sort of glass-like or transparent materials in later videos. As with physically based rendering, we'll just see how that goes and how much interest there might be. So I don't want to go too much into the theory of everything, and I think my thinking with that is if we go on later to talk about physically based rendering, then I will cover a great deal more detail about how light interacts with the surface of objects and how the diffuse intensity, essentially we're modelling a Lambertian surface and all of that kind of thing. We're not really going to talk about that today. I really just want to focus on the most basic thing. So this is really how we do the calculation for diffuse intensity, and we have seen this already in the previous video. So just to recap, if we have a light source, as shown here, which casts light along a vector that I've named L, okay, makes sense, and it strikes the object at a particular point, and the object has a normal given by the vector n, then the intensity of the colour from diffuse reflection is only going to depend on the angle between the incident ray from the light source L and the surface normal at that particular point. The key message here is that the diffuse intensity does not depend on the vector v, which is the vector from the observer to that point, okay? So we have the angle between these two vectors L and n, cos theta d for diffuse, is equal to simply the dot product of the vector L and the vector n, assuming they've both been normalized. And then we can go on to calculate an approximate illumination intensity based on this formula here. So I, diffuse along vector v, is simply equal to the incident intensity of the light, IL, multiplied by 1 minus 2 theta d, that's this angle here, over pi. And we talked about that in a previous episode, so I won't go over it in any great detail. But what this gives you a maximum intensity of equal to IL when n and L are parallel, when the angle there is 0, and a minimum intensity when the angle is exactly 90 degrees, which is really what you would expect. There are other ways of defining diffuse intensity. This is certainly not the only way of doing it, but it is the way I've done it, and it does work. As I say, if we go on to look at physically based rendering in a future video, then that's something we can go into in a great deal more detail. We could probably make a whole video really just talking about Lambertian scattering and that kind of thing, but as I say, that would be, I think, a step too far really for this video today. So the other component is specular intensity, and this is responsible for the sort of specular highlights. It's really what makes objects look shiny, and it gives real sort of cues to the brain about the shape of a surface or an object, as well as shadows and specular highlights. Those are really the two things that your brain interprets to understand shape in 3 dimensions. Okay, so, and specular highlights, you can think of them as being created essentially by like a thin film over the material. It's not necessarily physically the way things are working, but you can think of it that way. And so essentially it's a component that is simply added to the diffuse component to give the final result. Now the key thing to take home, the key message to take home from this diagram is that unlike diffuse intensity, specular intensity does depend on the vector v, which is of course the vector from the observer to the particular point. So as before, we have our light source, which is casting light along a vector L, striking a point on our surface, which has a normal vector n. And the first thing that we note is that this reflected vector here is given by the vector L minus 2 times the dot product of L and n multiplied by n, assuming that L and n are all normalized, and that will give us this vector here, R. And the actual specular intensity is simply then equal to, according to the Phong model anyway, the incident intensity of the light source IL multiplied by the dot product of R that we've just calculated and the vector v from the observer raised to the power of alpha, where alpha is simply a scalar number that represents the shininess, if you like, of the material. And this is an approximate model. It's not really trying to model the physics, but it does give the right sort of behavior to model specular intensity. And as I say, the key message here is this of course depends on the vector v. So as we change the angle from which we're observing the object or the surface, then we will change the specular intensity. And what we tend to get is that the intensity, the specular intensity, is very high for a very small range of angles around the vector v. And when obviously highest when the vector v is exactly coincident to the vector r. Okay, so I mean that's really as much as I wanted to cover for the theory at the moment for this video. When we come to implement these in code, we will see a little bit more about how these all work. Just really want to cover that the way we combine diffuse and specular intensity is simply by taking the sum. Okay, so the overall intensity observed along from the vector v from the observer is equal to the diffuse intensity ID for v plus the specular intensity IS for v. Okay, but of course the diffuse intensity doesn't depend on v at all, but the specular intensity does. And that's the very simple way that we are going to get the final result for the combination of diffuse and specular intensity. Okay, so that leaves the only last thing to cover is how do we model reflections? Well, we've already actually seen how we calculate the reflection vector, because we need to use that for the specular intensity, but here it is again, just for the sake of it. So we have a ray coming from our observer. Note we're not considering the light source, of course, in this case, because we're talking about how the light that the observer sees is reflected by the surface, not light from the light source. So we have our vector v from the observer, and we have the normal n to our surface here, and then our reflected vector r is simply given by v minus 2 times the dot product of v and n multiplied by n, assuming that v and n are normal. So the way we go about calculating reflections is we have this ray. This is what we call the camera ray in our ray tracing system. So it's the ray from our camera that has struck our object at a particular point. And then we calculate the reflection vector r, and then we simply cast the vector r out into the scene, and we check for intersections. We basically simply repeat the same process. So when we cast a ray into the scene from the camera, we check for intersections. If we find one, we then interrogate the properties of that object to determine what color that pixel should be. And we do exactly the same here. We cast a reflection vector into the scene, we check for intersections, and then we calculate the color contribution from reflection accordingly. And you can see how that will necessarily become recursive if we consider that we might have multiple reflections as shown here. So the vectors in yellow, of course, show the path of reflected light. So we have our initial vector v from the observer is then reflected to r1 and is then reflected to r2, and the formulas for those are, as you can see here, oh my apologies, that should be n2 not n1 there, that should be the dot product of r1 and n2 with n2. That's a typo, I do apologize, but you can see that from here, right? That's labeled n2 for the second object. And so what we do is we cast our ray from the camera, it strikes an object at a particular point, and we calculate the diffuse and the specular components at that point, and then we cast a ray according to the reflection vector back out into the scene, and that will probably strike or may strike another object. When it does so, we calculate the diffuse and specular component for that point on that object, and then we cast another ray according to the reflection vector from that object out into the scene, and we repeat that process again. And as you can see, the easiest way to implement something like this is necessarily going to be with a recursive algorithm. So we have an algorithm that calculates the color according to this ray, and then we call that same algorithm again to calculate the color from this ray, and so on. I think that will become much more clear when we actually come to look at the code. Okay, so that's really everything I wanted to talk about for the theory of how we're going to implement materials today. Now there is one other thing that I want to do, which may be slightly annoying for people following the series, I understand that, but I think will pay dividends in the end, and that is that I want to rearrange the code base that we've been constructing so far into a slightly better format. And to illustrate why I think that's worth doing, let's just have a look at a couple of diagrams I made about that now. So this is the code structure that we have now. We have our top level folder, and then within that we have main.cpp, capp.h, and capp.cpp, and so on. And then within that we have the QB ray trace subfolder that then contains all the scene, object base, and point light, and light base, and all of those things, okay? And then within that we also have the linear algebra library in an additional subfolder with all of its files. That's fine. But what is difficult about this is it means we end up with a great many files in the QB ray trace folder, which I think is really untidy and actually makes things quite difficult as we go on to add more shapes, and we're going to talk about adding materials and, you know, additional code to handle all of that today. It starts to get a little bit too complex. So what I'm going to do instead is rearrange the code like this. So we still have our top level folder with main and capp and so on, and then within QB ray trace we're going to keep the scene class, the camera class ray, and GTFM, these classes that we've written so far. But then I'm going to divide it into a number of subfolders for lights, called QB lights, which will contain everything to do with the lights, QB primitives that will contain all of the primitive shapes that we're going to define. Initially that's just the base class and then spheres and planes, but we will go on to do more. And then materials, QB materials, is going to contain the code we're going to write today for handling materials, and then the linear algebra library as before. Now I know this might be slightly irritating to people following along if you've been typing the code, but it's not that difficult to rearrange. All we have to do is make the folders and then copy the relevant files into those folders, and then simply make sure that we go through and modify all of our header files where we hash include anything to make sure it now goes to the different relative path. Okay, so that's pretty much the theory. I'm going to jump in now and start looking at the code, starting with the rearranging, and then we're going to go on to have a look at how we can implement classes to do basic materials. Okay, let's go. Okay, so I'm in the folder for my code. I've copied this into a new folder called episode 7 code. You don't have to do that if you're following along. You can just work with the directory structure that we've had so far. That would be perfectly acceptable. And the first thing I said that we're going to do is a little bit of rearranging of our code. So we're going to go into the QB ray trace subfolder, and what we're going to do now is create, well, let's just have a look. So I mean, this illustrates my point, right? We've got all of these HPP and CPP files all in here, and if we start adding the code for doing things like materials and new objects and all of that, this is rapidly going to become very cumbersome. So it makes a lot of sense, I think, to do a little bit of rearranging. So to do that, we're going to make our subfolders. So we're going to do qb make dir, and we're going to create qb primitives. I just want to make sure I spell that right. Okay, qb primitives, like so, and make dir qb lights, and make dir qb materials with a capital M, like that, materials. Okay, so if we look at that now, we see here that we have those subfolders as we would expect. So now we just need to copy the relevant code into the relevant subfolder. So we can do that using move. If you're not familiar with Linux, move simply moves files, cp for copy, mv for move. So we're going to move the files for, let's do our lights first. So we have lightbase.star, which we want to move into qb lights, like that. Okay, let's check. Yep, so those are gone, and then we also want to move pointlight.star into ./qb lights, like so. Okay, and we want to move our object base.star into qb primitives, like so. Oh, we didn't have to do / of course. Okay, /, and we're going to move also object plane.star into /qb primitives, and we're going to move object sphere.star into /qb primitives. Okay, so if we look at that now, looking much tidier already. In fact, that is everything that we need to do for actually moving the files. Now, of course, because we've done that, if we were trying to compile our code now, it will all fall apart and everything will go horribly wrong, because we need to modify our hash include statements everywhere where we have them to make sure that we're referring to the right relative paths. So let's have a look at doing that now. Okay, so the first place that we're going to start is in the scene class, so scene.hpp that we can see here. We obviously need to make some changes. Now QB image and camera, they stay where they are, but these now come from our different folders, so we need to change object sphere. It needs to be ./qb primitives /object sphere, like so, and this one the same, ./qb primitives /object plane, and this one can be ./qb lights / okay, and save that. That is everything that we need to change in our scene class for now. So the other thing then, now I'm in lightbase.hpp, which we've copied. Now because we've copied this into a subfolder, we need to change that path there to // so it goes to the previous folder and then into qblinal. And of course ray.hpp is now /ray.hpp, and this one is going to be /qb primitives /objectbase.hpp, just like that. Okay. Okay, now objectbase.hpp, very much the same. This is going to be .. and that's going to be .. and that one .. That's pretty easy. And objectplane.hpp, objectbase.hpp is fine, that's in the same folder, but gtfm is now from .. so save that. And finally objectsphere.hpp, so all we need to do is .. there for gtfm, and I think that is everything. When we come to compile it in a moment, we'll see if I've made any mistakes with that. Okay, so the other thing that we need to change to support our new structure, of course, is our make file. So this is the file that we've been using to control all our compilations. And all we need to do really is just add a couple of things here. So at the moment we compile from all the CPP files in the QB ray trace folder. That's fine. We're going to keep that. Okay, but we're going to add another line like so. And we're going to do $pat substitute %.cpp to %.o, $wildcard, exactly the same. And we're going to do /qb ray trace /qb primitives /star.cpp. Okay, so that will pick up all the files in the qb primitives subfolder. And then we use that / there, and we do the same thing, pat subst %.cpp %.o $wildcard %./qb ray trace /qb lights /star.cpp, just like that. And finally pat subs %.cpp %.o $wildcard ./qb qbraytrace qb materials star.cpp and close the brackets. Okay, and save that. So that is everything we need to do to our make file. So having done all of that, in theory, now hopefully if I've done it right, we should be able to compile our code without any problems. So let's try that now. Okay, so let's have a look. So we need to go back to the root, the top level folder there, and if we run make, hopefully that will go through and compile everything. We see it's picking up things in the relevant folders, it's QB primitives, QB lights, and so on. And if I run /qbarray, we should get the same result that we had at the end of the last video. And indeed we do. There we are. So that is exactly the result that we had at the end of the previous video, which is not tremendously exciting, but it does show at least that we have rearranged our code correctly, which is important. Okay, and I know that might be a little bit annoying for people following the video, but I think really it's going to pay big dividends as we go further on and as we do more things, particularly as we start implementing more shapes and the code that we're going to write today. So I think it's worth it. Okay, anyway, right, let's close that. So let's have a look at what we actually need to do for our code today. Okay, so the first thing that we're going to do to implement our material bases is in object-base.hpp. Obviously we need to modify the base class for our object so that we can assign a material to an object. Okay, and what we're actually going to do, this is going to look a little bit odd to begin with, but within our namespace just here, just before we declare our class object base there, we are going to forward declare, and I'm going to write this in, we're going to forward declare the material base class, and this will be overridden later. Okay, so we're simply going to define their class material base semicolon. Okay, and save that. Okay, and the reason we have to do that is because, as you will see, the material class needs to reference the object base class, and the object base class needs to reference the material class. So if you hash include everything, then you can get circular definitions, which causes all sorts of problems later on. And we need a function. We need one new function definition. We need a function here, function to assign a material. Okay, which is going to be bool assign material const std shared ptr. We've talked about those before. Type qbrt : material base. Okay, like that. A reference to object material, just like that. Okay, and save that. And then we need to declare the references. So what have we got? We've got our transform matrix. So just down there, we're going to have a reference to the material assigned to this object, which we're going to store as obviously std shared ptr, type qbrt : material base, just like that, m_p material semicolon, and we're also going to need a flag to indicate whether this object has a material or not. Okay, so bool m_has material equals false initially, and save that. Okay, so that is everything that we need to do in object-base.hpp. Now obviously if we were to compile that now, that won't really do anything. Let's have a look at object-base.cpp first. Okay, so object-base.cpp, we obviously need to add our function to assign a material, and we're going to put that down here. So put in a comment function to assign a material, right? Let's just put some blank lines in so we're not just typing at the bottom of the screen all the time. I always hate that. Right, so we have bool qbrt : object base : assign material, which accepts as input const std shared ptr of type qbrt : material base reference object material, like so. And this doesn't really need to do anything very much, just m_p material is equal to object material, so we just simply copy the reference to that, and then m_has material equals true, because we've now assigned a material, and then we simply return m_has material, and save that. Okay, that is everything that we need to do in object-base.hpp and object-base.cpp. Okay, so the next changes we need to make are going to be in scene.cpp. We're going to leave all the definition of our various objects and things just as they are for the moment. We will do some more interesting things with those when we come to that. But what we need to do, if we think about it, let's go down to where we actually have our rendering code, and that's this code here. And there's a few changes that I want to make to this. Now, first of all, at the moment, this does the whole check for intersections thing here. And what actually I want to do is to pull that out into a separate cast ray function, which I just makes things look a little bit neater. So before we do that, let's actually jump back to the HPP file. Okay, so in scene.hpp, we are going to add a new function, which is going to be, actually I declared it as public. Fair enough. Okay, so function to cast array into the scene. Okay, again, this is really just about making things a little bit tidier. So we have bool cast ray, qbrt : ray, okay, reference cast ray, std shared ptr type qbrt : object base as a reference to closest object, okay, because that's a return, so it's not const or anything. And then we have qb vector type double reference closest intersection point or int point, qb vector type double reference closest local normal, like so, and qb vector type double reference closest local color, just like that. Okay, and save. Right, let's go back to the CPP file. Okay, so in scene.cpp, first thing I'm going to do is declare this new function. Okay, so we have, this is our function to cast array into the scene. Okay, so bool qbrt : scene : cast ray, just like that. qbrt ray reference cast ray, std shared ptr qbrt : object base, reference closest object. Again, I just like tabbing things out like that because I think it's neat and tidy. And then we have qb vector double reference closest intersection point, and qb vector double, like so, reference closest local normal, and qb vector double reference closest local color. Okay, and there we are. So, no, do that again. Okay, there we go. Now the code we're going to put in here actually is quite a lot of the code that we've already written up here. So from here, so we take this code from there, min dist intersection found, we loop through all of the objects, calculate the distance of all of that, blah 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 blah, down to there. Okay. Now I just want to make sure I don't include too many things. So what we can do, in fact, okay, I need that there. So we can cut that code from there, and we're simply going to paste that into here. Okay, and let's just get the tabs right, so everything is neat and tidy. Okay, and this is simply going to then return intersection found, like that. Okay, so that's put all of that code then into, and I'm missing a letter there, that is qb vector, closest point. So that's taken all of that point code and just put that into a separate function, which makes everything a little bit neater. So if we go back to our main loop now, where we generate the ray for this pixel, okay, and then we set up that for our local object. And what we're going to do now instead is we now have qb vector double closest int point, three-dimensional of course, and this is going to be closest local normal 3, and QB vector double closest local color, also three-dimensional. And now we have bool intersection found is equal to cast ray, our new function. We simply pass to it camera ray, closest object, closest intersection point, and closest, if I could spell, closest local normal, and closest local color, just like that. Okay, right. And then before we have this if statement, if intersection has been found. Okay, now what we're going to do before we compute intensity of illumination, so we're going to put new code in here, and we are going to check if the object has a material. Okay, so if closest object m underscore has material, so if that flag is true, then we are going to do other stuff, right? Else we're going to do the code that we had before. We're going to probably make some changes to that, so we're going to come to that in a moment. Okay, so first of all, in this case we will use the material to compute the color. Okay, and very simply QB vector type double color, which is equal to closest object, like so, m underscore p material. So we access the material of the object, and we're going to call the compute color function from that material. We'll see that when we come to define the actual material in a moment. We're going to pass to that m object list and m light list. We'll talk about that in a moment. And then pass closest object, that's the current object we're dealing with, closest into point, like so, and closest local normal, for a point of intersection, the local normal, and camera ray. Okay, just like that, right? And that gives us our color, and then all we have to do is output image.setPixel x, y, color dot get element 0, color get element 1, and color dot get element 2, like so. Okay, now the other thing that I'm going to do, this code here, this actually calculates the diffuse intensity, and what I'm going to do is simply remove that, because we're going to recreate that code inside the material class, so there's no need to do that. So what we're going to do instead is we are going to define a static method. It's a basic method to compute the color, right? So we're going to have QB vector double material color is equal to QBRT : Materialbase : compute diffuse color. Now that's going to be a static method in the Materialbase class. We'll see that in a moment. We pass to that m object list, m light list, closest object, and closest intersection point, closest local normal, and closest object, m underscore base color, like that. Okay, semicolon, and then simply go back to here, output image set pixel x, y, and now map color get element 0, map color get element 1, and map color get element 2. Just like that, and save that. Okay, so we can see that makes everything really a lot neater in our main loop for our rendering. So if we find an intersection, we check if the object has a material. If it does, we interrogate that material to get the color for that point and set the output. If not, we use the compute diffuse color, which we're going to define as a static method in the Materialbase class, to get the color from the base color of the object, and we set the pixel accordingly. Okay, so let's save that. Right. Now before we can really do anything with that, we do obviously now need to define our Materialbase class. So let's have a look at that now. Okay, so I've gone ahead and created the Materialbase.hpp file in the QB Materials subfolder. So as before, we're going to declare our include guards hash and def Materialbase h hash define Materialbase h and hash and diff. Always good to have include guards. We then need to hash include a bunch of stuff. We need to hash include memory. We need to hash include /qb primitives /object_base.hpp. We need to hash include /qb lights /lightbase.hpp, and we need to hash include qb linalg /qb vector.h, like so, and hash include /ray.hpp. Okay, so that should be everything we need. We're putting this into our qbrt namespace as we've been doing with everything, and this is going to be our class Materialbase, like so. Save. Right, now we need to specifically declare our constructor and destructor. So in Materialbase, in our public declarations, and then virtual, because it's a base class Materialbase, so we have to override the destructor. Okay, now we're going to have a function to return the color of the material. So this is virtual qb vector double compute color. So this is the function that we just saw, except as input const std vector. I type std shared ptr of type qbrt object base reference object list, reference not star, sorry, reference to object list. Okay, so that is a reference to the list of all of the objects in the scene. We then have the same thing for all of the lights in the scene. Okay, shared ptr qbrt : light base, like so, reference light list. We then have const std : shared ptr of type qbrt : object base, and this is a reference to the current object. Always good to know what our current object is. We then have const qb vector type double, reference the location of the intersection point, and const qb vector double, so reference where have I got to local normal. Okay, that's the surface normal at that point, and const qb vector double, no, sorry, what am I doing? No, not that, const qbrt : ray, reference camera ray. Okay, and semicolon. So that's that. Then we're going to have specific functions which we're keeping in the public declaration here. So we have a function to compute diffuse color. Okay, so this is the one that is declared static, and that's very important so that we can access it without reference to a specific instance of this class. It returns a qb vector double, and it's called compute diffuse color. Okay, now the inputs to this are basically the same. We have our object list, our light list, current object, intersection point, local normal. So what we can do, let's just actually copy and paste that, save, you don't really need to see me typing all of that again. And let's just adjust the tabs, like so. And the only thing that's different now, this doesn't accept a camera ray. Instead, it accepts as input qb vector double, base color reference, base color, like so. Okay, that is nearly everything that we need. We need just one last thing. We need a function to cast a ray into the scene. Okay, so this is going to be bool cast ray, accepts as input const qbrt : ray, reference cast ray. Okay, const std : vector, the type, no, yes, yes, std vector type std shared ptr type qbrt colon object base. Okay, reference object list, like so, and const qbrt colon, no, I do apologise, const std colon shared ptr, like so, qbrt colon object base. So a reference to our current object, I'm just going to call it this object, okay? And then std shared ptr qbrt colon object base, and this will be a reference to the closest object, and so we're going to return that, it's not declared const, and then we'd have qb vector double reference, this is intersection point, like so, qb vector double reference closest local normal, and qb vector double reference closest local color, semicolon. Okay, right, and that's all of that. And then we just need a couple of public member variables. Well, we will need those, we don't need them right at the moment. And then just for completeness, I always like to define the private section there, even if I'm not going to use it. So let's save that. So that is materialbase.hpp for what we have so far. Okay, so I've simply gone ahead and created the materialbase.cpp file. We are, of course, going to hash include materialbase.hpp that we've just defined. Okay, like that. And then we need to define a constructor and destructor, and so on. So we have qbrt colon materialbase colon materialbase, our constructor. At the moment, I'm not going to do anything in there. And we have qbrt colon materialbase colon tilde materialbase. This is the destructor, and again, at the moment, we don't need to do anything. So we then have our function to compute the color of the material at the specified point. Okay, so this is qb vector double, this is the return type, it's qbrt colon material base colon compute color, just like so. And I am simply going to copy and paste. Okay, so this accepts as input, that's the definitions. This has saved me having to type all those out again. I've copied and pasted those from the declaration in the HPP file. Okay, so we can just leave that blank for the moment. And because this is our base class, we don't really need to do anything in here, except it does do a return class. So we do need to define an initial material color, which we're going to define as qb vector double and matte color size 3, and then we simply return that. Okay, return matte color. Okay, that is everything that we need to do for the compute color method in the base class. So the next function that we have, function to compute the diffuse color. Now this is declared as static, and we do need to do something here. So qb vector double, that's the return type, qbrt colon materialbase colon compute diffuse color. And again, I'm just going to copy and paste that in from the HPP file. Otherwise, you know, this video is going to be long enough as it is already. Okay, so that's the declaration for compute diffuse color. So what we're going to do here, this is actually the code that's going to go through and perform the calculations. So the first thing we need to do, so let's just put in a comment, compute the color due to diffuse illumination, like so. So qb vector double diffuse color, so we define that initially. Okay, we're going to have a variable double intensity, like so. We have qb vector double color 3, like so. And double red 0, double green equals 0, and double blue equals 0. We're going to use those as cumulative things. So bool valid illumination initially set to false, and bool elum found for illumination found also initially set to false. Now, I'm just going to put in some blank lines so that we can type more in the middle of the screen. So the first thing, we're going to loop through all of our lights. So we have our light list from the scene, a reference to it anyway, passed here. So we can simply do for auto current light in light list, just like that, which is nice, neat and tidy. So we do valid illumination, valid elum is equal to current light. And we're going to call the compute illumination method from the current light. We pass to an intersection point local normal object list current object color and intensity, like so. Okay. Now, if we have a valid illumination, then we do other stuff. So if valid elum, first thing we do is set elum found equals true. We do red plus equals color dot get element 0 multiplied by intensity. Green plus equals color dot get element 1 multiplied by intensity, and blue plus equals color dot get element 2 multiplied by intensity. Okay, just like that. Pretty straightforward. I did that already. Close that. Bum, bum, bum. And close our for loop. So that's it. And then out of the for loop now, if we found valid illumination at all, so if elum found, then we are going to set diffuse color, set element 0 to red multiplied by base color dot get element 0. And diffuse color dot set element 1 to green multiplied by base color dot get element 1. And finally diffuse color dot set element 2 blue multiplied by base color dot get element 2. Just like that. Okay, that's everything we need there. And then we simply return the material color. So return diffuse color, semicolon. Okay, and that is everything that we need. That is the very basic implementation of Materialbase. So if we compile everything now, we should get back to exactly the same result that we had before. So let's just save that. Let's go back to our terminal. Check we're in the right place we are. Let's run make clean because we've made some substantial changes. Okay, and let's run make. Okay, now we have an error, shared PRT, obviously that's not true. Scene HPP line 50, let's look at that. Okay, this is scene HPP line 50, shared PTR. A bit of a typo, sorry about that, shared PTR save. Okay, so save that, back to our terminal. And let's have a look. Okay, now we have quite a lot of stuff going on. Let's have a look. Invalid. So scene.cpp line 134. Let's look at that first. Okay, scene.cpp line 134. Yes, that's obviously meant to be a comma. Save, and I copied and pasted that, so that's going to come up again there and there. Let's just check in the HPP file for that. Yeah, okay, those are fine. So let's compile again. Right, okay, scene.cpp line 150, let's look at that, something going on there. Scene.cpp 150, alright, what have I got wrong? Okay, yes, right, my mistake, so let's just have a look at that. Okay, so we close from that one, and we close from that one, we've got an extra one there, haven't we? And that one, so 1, 2, 3, 4, 1, 2, 3, 4, return true. Okay, and okay, save. Let's go back. Make scene.cpp line 154. Yes, you see, I've made that same mistake there again. Okay, scene.cpp 154. That's this one. Scene.cpp 154. Yes, of course, comma there. And did I do that anywhere else? I don't think so. And we need a comma there as well. Save. Oh, careless. Right. Getting there. Okay, scene.cpp 157, 158, and 159. My mistake. Oh, Okay, apologies. So that is int point, local normal and local color. So let's just check where we've used those. Int point, local normal, local color, those are those. We can just tidy up the tabs there. Yeah, okay. Okay, of course, because closest intersection point, closest local normal, closest local color come from there, right? So we don't want to be declaring those again. Okay, so save that. Let's go back. Camera ray was not declared in this scope. Scene.cpp 164, let's look at that. Yeah, because of course I called it cast ray. Okay, save, that's cast ray there. Okay, and save that. Let's try again. Okay, yeah, and 173 as well, the same problem line, 173. I also called it camera ray. That is now cast ray. Okay, that's because I copied and pasted that. Apologies, that's very careless of me. Okay. Okay, so we still have this issue. Scene.cpp line 132. Okay, so back to scene.cpp. The one thing that we need to do is we actually need to hash include here. We need to include qb materials slash and we need to include Materialbase .hpp. Okay, and save that. Now if we go back, hopefully. Oh dear, no, that's even worse. Yeah, okay, well that's an obvious mistake. In Materialbase.hpp line 22, we can look at that. Materialbase HPP line 22, of course, shared PTR. So let's have a quick eyeball of those other mistakes. Yeah, see, the same thing there, shared PTR. And okay, I think we're fine. Let's compile again. Oh, well, we're getting there, look. Okay, object-based HPP, shared PTR and namespace STD does not name a template type. Object-based, did you forget to include hash include memory? I probably did. Okay, let's have a look at that. Okay, yes I did. So, okay, in object-based.hpp we also now need to hash include memory. I forgot that, my apologies. Everything else there should stay the same, so let's save. Okay, right, we're getting there. There's some repeated errors because I copied and pasted. So materialbase.cpp, the same problem line 18. Let's look at that. Okay, yeah, that's pretty obvious because I copied and pasted it. I should have anticipated that and save that. Okay, those are all small e's. You probably spotted that as I was typing, so sorry about that. Okay, and okay, let's just see what happens if we run it. And we get back to exactly the result that we had before, which seems an awful lot of work to simply get the same result that we had before. But we're going to go on in a moment to look at how we can implement the specular highlights and also reflections. And we wouldn't be able to do that if we hadn't done all of that work that we've done now. So anyway, let's jump to it. Let's have a look at how we can do, first of all, specular highlights. Okay, so far we've defined our base class for our materials, but we actually want to define a class that actually inherits from this to really make it do something. We did declare our compute diffuse color method here as static so that we can then use that from other things without having to actually declare an instance of the class. But what we want to do now is actually create, as I say, a proper class for materials. So let's go ahead and do that. Okay, so I've gone ahead and created a file called simplematerial.hpp in the QB materials subfolder, and we are, as always, going to do our include guards. Simple material hash define simple material h, like so, hash end if, just like that. And this, of course, goes into the QBRT namespace along with everything else. And this is going to be class simple material, which inherits from public material base, like so. And then we have our public things. We have our constructor and our destructor as always. Okay, we can leave the constructor just as it is actually. Anyway, so we have simple material constructor and virtual tilde simple material, like so, override for the destructor. We have that function to return the color, okay, which it declares virtual qb vector double compute color. This accepts as input const std vector, like so, of type std shared ptr, like so, qbrt colon object base, like that. Reference object list, reference not star, sorry, reference object list, just like that. And we have const std vector std shared ptr qbrt colon light base, reference light list, just like that. Const std shared ptr, try and get these right this time, qbrt colon object base, reference current object, okay, just like that. And const qb vector type double, reference intersection point, and const qb vector double, that's local normal. Okay. Oh, and one last thing. So const qbrt colon ray, reference camera ray. And not forgetting the override keyword at the end. Okay, so that's going to be our main function there. We also have a function to compute specular highlights. Okay, so in our base class we defined a virtual compute color function that's simply being overridden by each class that inherits from that. So that's what that does. Now this one, compute specular, is specific to this class. So qb double compute specular, like so. And this basically accepts the same things that we have from here. So what I'm going to do is simply copy and paste from there to there, like so. Let's just tidy those up. And just check we've got this right, that it is exactly the same. The one thing we don't need in compute specular is our reference to current object, so we get rid of that. So we have object list, light list, intersection point, local normal, and camera ray, just like that. Okay, there we go. Okay, and we have some public member variables that we need to declare. So we have public, we have qb vector double m underscore base color, which we're going to initialize like so to 1.0, 0.0, 1.0. We have double, I'm going to define this here, we're not going to use it for the moment, m reflectivity, I'm going to come back to that, and double m shininess, 0.0, like so. Okay, that is everything that we need for simple material.hpp. So let's go and look at simple material.cpp. Okay, so I've gone ahead and created the file simplematerial.cpp in the same folder as simplematerial.hpp. First thing we're going to do is hash include, of course, simplematerial.hpp that we've just defined. And we need to declare our constructors and destructors, simple material, neither of which do anything, but we have to declare them anyway. Simple material colon till simple material. Okay, now function to return the color. Okay, so this is qb vector double, that's the return type, belongs to qbrt simple material colon compute color. And I'm going to copy and paste from the header file here. Okay, just like so, and then just tidy up the tabs a little bit, keep things looking nice and tidy. If you do look at this code on GitHub, I'm well aware that the tabs do go a bit wrong because I use a tab space of 2, which is different. Anyway, so there we go. And this is compute color. Now we're going to need a number of different things first of all. So first of all, let's define the initial material colors first. So I'm going to define them all. QB vector double, material color, right? 3, okay. QB vector double, we have a reflection color, color due to reflection, but we're not going to talk about that just yet. QB vector double diffuse color, okay, which we've covered already, like so. And we're going to have QB vector double SPC color for specular color, okay, which is the one we're going to talk about now. The first thing that we do is compute the diffuse component. Now we can do that, that's really easy. It's diff color is equal to compute diffuse color. We just call that function from the base class. We pass to it object list, light list, light light list, current object, intersection point, local normal, and m underscore base color, just like that. Okay, that's pretty easy. Now we are going to compute the specular component. Okay, so if m shininess is greater than 0, so if we want shininess, then we do SPC color equals compute specular, and we pass object list, light list, current object, intersection point, local normal. My apologies, of course, we don't pass current object, we don't worry about that in this case. So compute specular, we have object list, light list, intersection point, local normal, and camera ray. Okay, just that, pretty easy. And all we need to do then is to combine them. So we add the specular component to the final color, which at the moment is simply the diffuse color. So final color is matte color is equal to diff color plus SPC color, just that. And then we're simply going to return matte color. So that's pretty straightforward. So that's the overriding of the compute color method from the base class, which is going to simply at the moment compute the diffuse color. If we have shininess greater than 0, we compute a specular component, and then we add those together, and there we go. Now, of course, initially that's not going to do anything, because we need to go on to declare our compute specular function. So let's do that. So we have function to compute the specular highlights, right? Let's put some blank lines in so we can type in the middle. So return type is QB vector double, it's QBRT : simple material : compute specular. And as before, I'm just going to copy and paste that from the code that we wrote in the header file, which is, I think, a lot tidier, hopefully, and will hopefully reduce the chance of errors, though that doesn't always work out. Okay, so this is the code that's actually going to compute our specular components, right? So first of all, we need to declare some stuff. We need QB vector double SPC color. Okay, so specular color, right? We need double red set to 0, double green equals 0, and double blue equals 0, just like so. Now we're going to loop through all of the lights in the scene, right? So for auto, current light in light list, like so. Now, first off, we need to check for intersections with all objects in the scene. Okay, so what we're doing here is checking that we have a clear path from where we are, all objects in the scene except the current one. Okay, so we want to know if we have a clear path. Now, in fact, okay, we don't check for the current object, we just check for all objects in the scene. Okay, so, right, double intensity equals 0.0, like so. We need to construct a vector pointing from the intersection point to the light, right? So let's have a look. We do that with QB vector double, and call it light dir, which is equal to current light get its location, minus intersection point, okay, like so, dot normalized, just like that, okay? So that's pretty easy. Now we're going to compute a start point, is QB vector double start point, which is equal to the intersection point plus light DIR multiplied by some small number, 0.001 I've used, okay? And then we construct an array on the point of intersection to the light, okay? And I just realised that, of course, should be point. Okay, apologies for that, right. So QBRT, array, I'm going to call it light ray, makes sense, right? We go from start point to start point plus light DIR, just like that. Okay. Now, the interesting bit, we're going to loop through all objects in the scene to check if any obstruct light from this source. Okay, so now we need to declare some stuff. We have QB vector double point of intersection, POI, tabbing going on to keep it nice, QB vector double POI normal, so the normal at the point of intersection, like that, QB vector double POI color. Okay, those are all three-dimensional vectors, just like that, and all valid int initially set to false. And then we're going to loop through, so for auto scene object in object list, just like that, if scene object, scene object, we call the test intersection function for the object, we pass light ray as the ray that we're using, POI normal, and POI color, just like that. Okay, so if that's true, then we have valid intersection equals true, and we can break out of the loop. So this is, you'll notice, pretty much exactly the same code that we had for casting shadows. And we as soon as we detect that one object has an intersection with this light ray, then we don't need to check anymore. So break can give us some efficiency savings. So then we come down to here, and if no intersections were found, then proceed with computing the specular component. Okay, so if not valid int, so if we found no intersections with objects, okay, so we need to compute the reflection vector. This is QB vector double, let's put this back in the middle, QB vector double D is equal to light ray dot m underscore lab, okay. QB vector double R is the reflection vector D minus, open brackets 2 times QB vector type double colon dot for the dot product D and local normal, like so, multiplied by local normal, close brackets, and semicolon, and R dot. It's important to normalize that, R dot normalize, right? Pretty easy, and we're going to compute the dot product that we want, okay? So QB vector double V is equal to camera ray dot MLAB, that is the ray from the observer, okay? V dot normalize, just make sure, it probably is normalized anyway, but it doesn't hurt, double dot product is equal to QB vector double colon dot of R and V, okay? Now, only proceed if the dot product is positive, okay, so if dot product greater than 0.0, we do stuff, otherwise we don't. We're going to, intensity is equal to m underscore reflectivity. I've just used that as a constant at the moment, so we have to find an M reflectivity value for our materials, multiplied by, now we need to raise this to the power, so using STD POW, and we raise dot product to the power of M shinies, semicolon. We drop out of there, and here we're going to do red plus equals current light M color dot get element 0 multiplied by intensity, like so. Green plus equals current light M color get element 1 multiplied by intensity, and blue plus equals current light M color get element 2 multiplied by intensity, just like that. Okay, and then the final bit, we're going to create the final output with SPC color dot set element 0 to red, SPC color dot set element 1 to green, and SPC color set element 2 to blue, red, green, and blue, and then finally return SPC color. Okay, that is the whole function for computing specular highlights, and that is everything that we're going to put into our simple material class for the moment. Now, the next thing, because obviously we can try compiling that now, and that's quite a good idea. Let's just see if we've got any errors. Okay, so I'm in the main folder. We made some big changes. I'm going to run make clean first. Run make. Okay, okay, right, it's always worth checking. Simple material.hpp line 9, expected class name before then. Golly, okay, let's look at that. Simple material.hpp, simple material.hpp line 9. Oh, what have I done wrong there? That seems pretty basic. Okay, yeah, I forgot that hash includes. That's pretty silly of me. Of course, we have to hash include Materialbase.hpp, obviously. Okay, and save that. That should fix that problem. Right, we still have an error. Diff color was not declared in this scope because I spelt it with a double F, which is obviously wrong. Simple material.cpp line 36. Okay, simple material.cpp line 36. Here we go. Yes, diff color is with a single F, of course. I defined it there. Save that, and let's try. POI color was not declared in this scope. It's the same. Simple material line 75. Let's have a look. POI color. Okay, yep. POI color. Save that. Let's check. What was that? Simple material CPP line 76. Okay. Right, let's have a look at that. The problem is probably on 75. Okay, yep, simply missing a bracket there. That's pretty straightforward. And make. Okay, that'll, and if we run that, we shouldn't see anything different at the moment. And indeed we don't. Okay, that's good. So, now, the reason we don't see anything different is, of course, we haven't actually assigned any materials to anything. So let's have a look at doing that now. If we go to scene.cpp, so scene.cpp, right up here at the start, underneath where we were just before, yep, setup. We configure the camera, so right here at the top, in the constructor for the scene, we are going to create some materials, right? So auto test material is equal to std : make _ shared qbrt : simple material. Right, and to make that work, we need to obviously include simple material here. We don't actually need material base. So we can change that to simple material.hpp here, and we're going to create qbrt : simple material. Just like that, okay? Now to start with, I'm simply going to create just one test material like that, and we're going to set up the materials, right? So test material, we set first of all M base color. I'm going to set that to qb vector double, std vector double, 0.25, 0.5, 0.8, okay, semicolon, that's a nice blue, and we're going to define, it has a capital M, apologies, so test material M reflectivity, we're going to give it a reflectivity of 0.5, and test material M shininess equals 10.0 initially. Okay. So now let's have a look. We construct our spheres, we construct our plane, we modify our spheres, and then we've got the modify the spheres, we set the color of the spheres here. Right, so after we've done that, I'm going to put this in here before we do anything to do with the lights. We're going to assign materials to objects. Okay, so simply do m underscore object list at 0, take the first object, and we are going to assign material test material. Just like that. Okay, so that will now assign a material to our object, the first object in our list, which is going to be our left-handmost sphere, I think. Okay, so in theory, that means we should now see, when we run that, we should get the specular highlights. So let's just have a look. Because we've set a material, we've already modified the code that we need. So if we go back to here, let's run make. Okay, /qbarray, and well, okay, nothing has changed. So why is that? Okay, so after a quick break and a little bit of rummaging about, I did find what the problem was, and if we just have a look, the problem is here in we are in simple material.cpp. And the problem I was having actually came down to this code here, where we cast the light ray into the scene and check for intersections. And I've rewritten it as now as valid int is equal to the result of calling the test intersection function on the current object. And if valid int is true, then we break. And if no intersections were found, then we proceed with computing the specular component exactly as we wrote before. So now if we save that, and let's just have a quick look at the scene class. So in the scene.cpp file, we've defined our material here, specified its colour to a nice shade of blue, we set the reflectivity to half, the shininess to 10. I have altered the spheres as well. I altered the transforms just to set the scalings to be a half and a half and a half in x, y and z in all three cases, so that means they're actually just spheres. But other than that, I haven't made any other changes there, and that's not important. I've just done that as part of my debugging, but it shouldn't actually make any difference. So if we go to the terminal window, okay, so let's just run, because we've made those changes, run make clean, let's just run make, compile everything. Okay, and let's run qbarray. Okay, so we find that now we have the blue sphere over here on the left now has the specular highlights as we would expect. Now we have a red light, a green light and a blue light, so we see the red, green and blue components of the specular highlights, but clearly we can see that that is working as it should, which is good news. Okay, so what about reflections? I talked about how we need to implement a recursive algorithm to make that happen. So we, when we strike an object, we cast another ray off along the reflection vector. When that strikes an object, we calculate the diffuse and specular components of that, plus the new vector, and so on. So let's have a look at how we do that in code. Right, so we are going to go back to, here we go, back to, not that one. Okay, so back in simple material.hpp, we already defined a variable there for our reflectivity, and we have in fact actually already used it now. Okay, so I've gone into the Materialbase.hpp class, and I'm going to put the code for computing reflections into the base class for the materials, because it's something that we might want to do over a number of different materials that we're going to create. So the first thing that we need is a function. So let's look at that. We're going to need find here function compute the reflection color. Okay, and that's going to return QB vector double. And that's called compute reflection color, like that, and it accepts this input const. Now this is actually exactly the same. Yes, it's actually exactly the same as the syntax for compute color. So we're going to just copy and paste from there to save a bit of time, like that. And let's just check this. Instead of camera ray, we call it incident ray, so that we don't get confused. And we have local normal, intersection point, current object, light list, and object list. Okay, just like that, right? And we also need some public variables. So we need a counter for the number of reflection rays. Okay, and we're going to declare these as inline static int m_max reflection rays and inline static int m_reflection ray count. And the reason for declaring these as inline static is because we only want one instance of all of these, regardless of how many instances of material there are. It's like defining a static function. With a static function, we can refer to it without referring to a specific instance of the class, and that's the same with a static variable. Inline simply means that we can assign values to it. So that's pretty straightforward. So that's all that we need to change in Materialbase.hpp. So let's save that and go to Materialbase.cpp. Okay, and here we are going to define our function to compute the reflection color, which is going to go here. And here we go. Function compute the color due to reflection. Okay, so it returns QB vector type double. It's QBRT colon Materialbase colon compute reflection color. So I'm simply going to copy and paste from the header file, so I don't need to type all that out. Just tab those out nicely, like so, and there. Okay. Okay, so first thing we need to do, in here we're going to define QB vector double reflection color, which is a 3-dimensional vector. Okay, we need to compute the reflection vector. So scroll that up to the middle of the screen like so. So compute the reflection vector with QB vector double d is equal to incident ray dot m_lab. Okay, and then we have QB vector double reflection vector is equal to d minus 2 times QB vector by double colon dot for the dot product of d and local normal multiplied by local normal, just like that. Okay, that's our reflection vector. We need to then construct the reflection ray, okay, which we are going to do as QBRT colon ray, reflection ray from intersection point to intersection point plus reflection vector, like so. Okay, and then we're going to cast this ray into the scene and find the closest object that it intersects with. Okay, so we have std shared ptr type qbrt colon object base. Closest object, going to use that to store a reference to the closest object. Then have QB vector double closest intersection point, like so. 3 QB vector double closest local normal. 3 QB vector double closest local color. 3, just like that. And then bool intersection found is equal to cast ray reflection ray object list current object closest object closest intersection point closest local normal, and closest local color. And save that. Now, we have already declared our cast ray function, but we haven't actually done anything with that yet. If we go back to the CPP file, we've got our constructors, compute color, compute diffuse color, compute reflection color. We need to insert our code for cast ray. So let's just do that now. Function to cast array into scene. qbrt : Materialbase : cast ray. And I'll just paste that in then from the header file and just put some nice tabs in for everything. Okay, like so. Now this is very, very similar to the code that we had before, so we are going to test for intersections with all of the objects in the scene. So we have qb vector double int point 3 qb vector double local normal 3 and qb vector double local color 3, just like that. Double min dist is equal to 1e6 to begin with. Intersection found equals false. And then we simply do for auto current object in object list. List like that. If current object is not equal to this object, most important. So this object we pass here, that is the object that we're dealing with. So if we're not indices, it really avoids testing for self-intersections, then we simply have bool valid int equals current object test intersection, like so, cast ray int point local normal and local color, just like that. If we have a valid intersection, so if valid int set the flag to show we found an intersection. Okay, intersection valid equals true, like that. Compute the distance between the camera, or the intersection point, between the source and the intersection point. Okay. Double dist is equal to int point minus cast ray dot m underscore point 1 dot norm. Okay, gives us the norm of that. Store a reference to this object if it is the closest. Okay, pretty simple. So if dist is less than min dist, then min dist equals dist. It's a pretty standard way of doing things. Closest object, to store a reference to the current object, like so. Closest int point equals int point, like that. Closest local normal equals local normal. And closest local color equals local color, just that. 1, 2, 1, 2, 3, 4, 1, 2, 3, 4, and return intersection found. Okay, that is everything we need for cast ray. So we're using that here. If we go back to the compute reflection color function, we use the cast ray function. So if we get to here, we want to compute the illumination for the closest object, assuming that there was a valid intersection. So compute illumination for closest object, assuming that there was a valid intersection. Okay. QB vector double map color 3 for material color. So right, if intersection found and m underscore reflection ray count less than m underscore max reflection rays, like that, then, okay, we're going to do stuff. So here, what we're going to do is, as long as m reflection ray count is less than m max reflection rays, then we will continue doing this when we find an intersection. So we check for intersections with objects in the scene. If we find one, we check this. And this is because we're going to call this recursively. We don't want to end up in an infinite loop. If we don't count how many times we come through that, then we might get into an infinite loop. So we want to increment the reflection ray count. Okay, m underscore reflection ray count plus plus. Now we can do that because m underscore reflection ray count was declared as inline static, which means it is only ever one instance of that variable. So it doesn't matter which class or instance of the class we're in. When we increment this, we're incrementing that one variable. So it will always be the right value, which is pretty cool. Okay, now we're going to check if a material has been assigned to this object. Okay, so if close this object, m underscore has material, if that's been set, right, then we're going to use that material, use the material to compute the color, right? So in that case we just have map color is equal to closest object m underscore p material. So we get a pointer or a handle to the reference to the material, and then we call the compute color function on that material, passing object list, light list, closest object, closest interpoint, and closest local normal, and reflection ray as the inputs. Okay, so you can see how that's going to be a recursive loop. So we're in an instance of the material cast, and then we cast the reflection ray. When it hits an object, we then interrogate the material of that object, and we call the compute color method on the material of that object. So that is essentially a recursive function. It's going to come back through this same code again, and it's going to do that until m underscore reflection ray count is equal to m underscore max reflection rays. Okay, it might be a little bit confusing, but hopefully if you think it through, it will make perfect sense. Okay, so in the case that a material has not been assigned, in that case we're not going to do anything at all. No, yes we are. Okay, in that case we're simply going to calculate the diffuse color QBRT : Materialbase : compute diffuse color, and pass object list, light list, light list, closest object, closest interpoint, closest local normal, and closest object m underscore base color, like that. Okay, and that is the end of there, right? And then close that one. Now in the event that we didn't find an intersection, or we've reached the maximum count, then we simply leave map color as it is. We don't do anything, we don't need to write any code there. Okay, and then we have reflection color is equal to map color, just like that. Return reflection color. Okay. And that is the end of the function. That is everything that we need to implement reflections. Okay, so if we have a look at that, we've put that into the base class. So what we need to do is we now need to have a look back at the simple material.cpp. Okay, so we're back in simple material.cpp, and we need to look at where we compute our color. So we have our function here to compute color. It at the moment computes the diffuse color, and then it computes the specular component. What we're going to do is put in here to compute the reflection component, like so. Okay, so this is going to give if m reflectivity is greater than 0, so if there is some reflectivity, then ref color for reflection color equals compute reflection color, which we're calling the function that we just wrote in the base class, object list, lig light list, current object, intersection point, local normal, and camera ray. Okay, let's check I've got that right. Yes, and we are then going to combine specular. No, in fact, no, we're not. Oh, interesting. Combine reflection and diffuse components. Okay, so we simply have matte color is equal to reflection color multiplied by m underscore reflectivity, like so, plus diff color multiplied by 1 minus m underscore reflectivity, like so. I think I've done that right. Yes. Okay, so that is essentially the weighted mean of the colour due to reflection and the colour due to diffuse scattering. And there are different ways of going about doing it, but this is the way I've done it, and I think it gives pleasing results. And we are only talking about approximations here. We're not doing anything super exactly, so I think that's fine. And then we've got our shininess there, which calculates the spec colour, and then we have, at the moment, let me just change this code here. We need to add the specular component to the final colour. So what we actually have is that matte colour equals matte colour plus SPC colour, like that, because we've defined matte colour here as the weighted mean of those two, and then we add the specular component to that and return matte colour. Notice we can't do matte colour plus equals because the plus equals operator isn't overloaded in the QB linear algebra library for the QB vector class. Okay, so that should be everything that we need to do. So let's have a look now. We've already defined a reflectivity for our object in order to get the specular to work. So if we compile now, let's see if we have any errors. Okay, and we do local normals, obviously spelling mistake, simple material.cpp line 33. This is simple material.cpp line 33. Yep, there we go. Local normal, save that. Let's try again. Okay, local normal and save. Right. Okay, we compile without error. So let's have a look now what we get. Okay, so we have our diffuse component and it's got a little bit darker, but I'm not actually seeing any reflections. Okay, now the reason is fairly obvious. We need to define a max reflection rays. So that actually goes in the constructor of Materialbase.cpp. We're going to define here m underscore max reflection rays is equal to 3. Okay, and m underscore reflection ray count is equal to 0. Now, that's still not everything that we need to do. The other thing that we need to do is we need to look back at the scene class. Okay, so back in scene.cpp, and let's go back down to our render code here. And the one thing that we need to remember to do just before we compute the color in the event that our object has a material is that it is very important that we reset our counter. So qbrt : Materialbase : m underscore reflection ray count equals 0. Okay? Save and save that. So that we can do that because m underscore reflection ray count was declared as inline static, so it doesn't belong to any specific instance of Materialbase. So we can simply call it even without reference to any particular instance of the class, and we can set it to 0. And what that means is for every pixel, as we go through it, we're going to reset that to 0, and then for that pixel we increment that every time we cast a reflection ray. It increments by 1, and once it reaches the max number of reflections that we want to allow, then it will end that recursive loop from happening. So that just makes sure that we don't get stuck in an infinite loop when we have perfect reflectors that might be completely parallel. Now, one other thing that I just want to do that I think is quite good, because our code is a bit slow now, it's nice to see what's going on. So I'm going to just change this loop around. Okay, so here we have int x. We're going to change that to y. So we change x to there, change all that to y, and change this one to x. So change the sequence in which we're going through those, and in here I want to display progress. Okay, so in there we're simply going to do std cout, and we're going to put processing line space y of y size. Okay, so that will give us a simple display to the terminal to say which line we're doing, so we can see what's happening as we go. So let's just go back to our terminal, compile and run it, and let's see what happens. Okay, so we can see our progress as we go, and now let's have a look. And there we go, we now have a sphere with reflections and with highlights, which is exactly what we'd want. Now, of course, no other surfaces here at the moment are reflective, so we don't see anything tremendously exciting, but clearly it's working. So let's just have a look at that. Let's make the rest of the spheres reflective as well. We've got test material. We're going to create another one, test material 2. So std make shared qbrt : simple material, another instance of simple material, qbrt simple material. Okay, and in fact that code is going to be the same for every one. So we can just copy that to there. Auto test material 3 is equal to the same thing, and auto floor material is also equal to the same thing. So now we're going to set up those materials. That's the first one, and I'm going to set it to 0.1 and a shininess of 10, and have test material 2 m_base color equals qb vector double std vector double and color 1.0, 0.5, 0.0. Okay, test material 2. Oops, there we go. Reflectivity is 0.75, okay, and test material 2 shininess equals 10.0, and test material 3 m_base color is qb vector double std vector double, and we're going to set this to 1.0, 0.8, 0.0. Test material 3 m_reflectivity 0.25, and test material 3 m_shininess equals also 10, and then we have floor material and base color is qb vector double std vector double, and we'll make the floor white. Okay, floor material and reflectivity 0.5, and floor material m shininess equals 0. Okay, so let's look where we assign the materials. Modify the spheres, assign materials to objects. So that's those. So we're going to have m object list.add1 assign material, and we'll make this one test material. That one at the top there, test material 3, and m object list add2 assign material and test material 2, like so. And then we're going to assign also the floor material, so we simply have object list at 3 assign material floor material. Okay, so that should pretty much give what we want. So let's just save that, run make. Okay, and run pbarray, and we can see how it's progressing. And with reflections you can see how it gets quite slow, and that's because it's having to do all the recursive looping and everything, and so it's quite nice to have a progress indicator, I think. And there we go. So we have 3 beautiful reflective spheres with specular highlights and reflections in the floor. And I think that's actually pretty cool, so feel free to play around with that. You can do all sorts of things with it, change the shapes of the spheres, do whatever, you know, like we've done before. But there we go, so we've implemented basic materials with a diffuse component, with a specular component, and with a reflection component, and we've done it in such a way as that they are really flexible, and it's possible to change the parameters and generally set that up how you wish. Okay, so remember, in this particular scene here we have 3 lights which are red, green and blue. For the example pictures that I showed before on my channel, I actually had made the lights slightly whiter, so this is why the specular highlights here look a bit different. But as you can see very clearly, everything is working. You can see that we get multiple reflections exactly the way we should, and yes, well, there we go. I really think I've spoken for long enough about this now. I do apologise for this becoming really rather a long video. It became a lot longer than I thought, but as I say, we have covered a lot of ground and a lot of material, and I think we're well on our way to putting our code together in a really nice way and creating a really nice flexible foundation onto which we can build a really interesting ray tracing program. So anyway, the next thing that I want to look at will be different shapes, in particular cones and cylinders, so that will be coming in the next episode, so do keep an eye out for that. And just leaves me to say that if you've liked this video, please do remember to hit that like button, and if you haven't done so already, please consider subscribing to my channel so that you don't have to miss any future videos. Thank you very much. Anyway, listen, it's been a real pleasure. Congratulations on making it this far through the video. If you've watched all of it through, that's brilliant. Well done. And yeah, anyway, listen, it's been a pleasure. I hope you've enjoyed it and found it useful, and I really look forward to seeing you in the next video. Thank you very much for watching. Bye.